A copper calorimeter can with mass 0.100 kilograms contains 0.150 kilograms of water and 0.0180 kilograms of ice in thermal equilibrium at atmospheric pressure. If 0.750 kilograms of lead at a temperature of 255 degrees Celsius is dropped into the calorimeter can, what is the final temperature? Assume that no heat is lost to the surroundings and that all of the ice melts. Let's begin by sketching the scenario. So we have a copper calorimeter can, which I'll represent with this cylindrical looking object here. It says this copper can doesn't exchange heat with the environment. So with that said, let's assume that this can is thermally insulated. So it's like a perfect insulator. So I'll just illustrate that in my picture. And I'll put some hatch marks there to indicate for myself that this copper can will not be exchanging any thermal energy with its environment. Now inside this copper can, we have water in thermal equilibrium with ice. So I'll represent the ice as a block, and I'm kind of representing the water as kind of this smaller bluish cylinder. Now we know the copper can has a certain mass, so I'll label that as m sub c for the mass of the copper. And so the mass of the copper is 0.100 kilograms. The water has a certain mass, so I'll label that as m sub w. So the mass of the water is 0.150 kilograms. And the ice has a certain mass, so I'll label the ice m sub I, and that mass is 0.0180 kilograms. Now the problem says that the water is in thermal equilibrium with the ice at atmospheric pressure. Thermal equilibrium means they're at the same temperature. So water currently is coexisting with ice at the same temperature. Well, if it's at atmospheric pressure, that means the temperature is 0 degrees Celsius, which we will say that that is equivalent to 273.15 Kelvin. We also know that we have a certain quantity of lead. I'll indicate that with an m sub L for the mass of the lead, and the mass of the lead is 0.750 kilograms. The lead is at an initial temperature, which I'll indicate the temperature of the lead as T sub 0 L at 255 degrees Celsius. So the lead is dropped into the calorimeter can. So I'll indicate those items in our system. So we have the ice in our can. We have the water in our can. And we have our can itself. Now let's look at this. So our goal is to find the final temperature of the system. So the lead is at a significantly higher temperature than the ice-water mixture. Also, the lead is significantly more massive than the ice-water mixture. So let's do this. Let's assume that the ice is all going to melt because it is not a lot of mass. And since the specific heat of lead, though, is much less than the specific heat of water and the specific heat of ice, let's assume that the lead's temperature will drop down significantly. So much so that it will not cause a phase change of the water to steam or vapor. So yes, these are some assumptions that we're making. If our assumptions don't pan out, then we would end up with some nonsense results, like maybe numbers that don't make sense. But let's go with those assumptions for now. So we are going to assume that after some period of time passes, the three items, including the can, will reach a state of thermal equilibrium. So what that means is if it reaches a state of thermal equilibrium, the water, the ice, and the lead will all arrive at the same final temperature, which is unknown. That's what we're going to have to determine. We should realize that being at a higher temperature than the ice and the water, that the lead is going to lose some of its thermal energy, while the water and the ice will gain some of that thermal energy. Let's use temperature energy diagrams to view this process. Let's start off with the temperature energy diagram for the lead. So the vertical axis will correspond to the temperature, and we'll just do the temperature in Kelvin. Now remember, a Kelvin temperature is just shifted from a Celsius temperature by 273 degrees. So this will keep, by being in Kelvin temperature, this will keep everything above our energy axis. So let's say that our lead starts off with a certain initial temperature, which we call T naught lead. And the lead is going to end up at a certain final temperature, which we'll just call T. So we'll say the lead starts off at a certain energy, and the lead will cool until it reaches our final equilibrium temperature. So I'll just do this as EL for the energy of the lead at that time. In this process, since there is a loss in temperature, we know that the lead is going to be losing energy, losing thermal energy, which I'll call QL. Now, that thermal energy isn't really lost. It's just being exchanged with other objects in the system. But let's call this heat exchange. Let's call it ML for the mass of the lead times the specific heat of the lead times the temperature change. Final temperature minus the initial temperature of the lead. We'll assume that the lead doesn't experience a phase change. Let's now look at the temperature energy diagram for the liquid water. Again, the vertical axis is temperature, horizontal axis is energy. Since I'm drawing multiple diagrams now, it might be useful to just label our axes with subscripts to keep track of the quantities that we are interested in. Since the water is in thermal equilibrium with the ice at atmospheric pressure, we can assume that the water starts off at an initial temperature of 0 degrees Celsius. And the final temperature of the water, we're going to assume that the final temperature will be some temperature above the initial temperature. It'll be the same temperature as the final temperature of the lead, T. So we'll say the water starts off with some initial state of energy and ends up at some final state of energy, gaining energy. So to illustrate that in my picture, I am just going to do this linear line. And this is indicating a change of temperature that is going to be positive. So this is the change of temperature of the water. And so since the water is already in liquid form and we're assuming that it is not going to go into gaseous form, there's not going to be any phase changes, I know that this positive temperature change means that the water is going to exchange heat with the environment given by the mass of the water, the specific heat of the water, and the temperature change of the water. Final temperature will be T. Initial temperature of the water is T, not W. And don't forget that initial temperature of the water is the same as the initial temperature of the ice, which is 0 degrees Celsius. Now let's look at a temperature energy diagram for the ice. We should bear in mind that the ice is going to experience a phase change from solid form to liquid form. So the ice starts off at the same initial temperature of the water. For now, I'll just label it as T sub naught I for the initial temperature of the ice. The ice will arrive at the same final temperature of the water and the lead. I'll call that T sub I. But remember, the final temperature of the ice equals the final temperature of the water equals final temperature of lead equals T. So the ice starts off with an initial state of energy. It is at 0 degrees Celsius and it is experiencing a phase change. So while it's experiencing a phase change, there can be no change of temperature of the ice. After all of the ice is melted, it will then increase in temperature. So we have a positive temperature change for the ice. And notice that initially we have a phase change that is going to consume some energy. I'll just say when the phase change is done, I'll call that state of energy E1I for the state 1 of the ice. And it'll arrive at a final state of energy, which I'll just call E sub I. So there's two processes going on for the ice. There is a phase change and there is a temperature change. So for the ice, the heat exchanged, we have to consider those two processes. So the heat exchange of the ice is the heat due to the phase change of the ice plus the heat due to the temperature change of the ice. So we could represent that as mass of the ice times the latent heat of fusion for ice, which is the same as the latent heat of fusion for water. There is a plus sign in front of that because this is energy needs to be added to change the phase of ice to water. And then this is plus. Now all of that ice is melted. So this is going to be plus the mass of the ice, but now this is going to be the specific heat of water, because all of the ice is now melted and is a liquid, times the temperature change, final temperature T, minus the initial temperature of the ice, which is the same as the initial temperature of the water. And now let's take a look at the temperature energy diagram for the calorimeter. So again, the vertical axis will correspond to the temperature the calorimeter can, which I'll label with a subscript C. The horizontal axis will correspond to the energy the calorimeter can, which I'll label with a subscript C as well. Now, just like the water and ice, the calorimeter can will start off at a certain initial temperature, which is the same temperature as the water and the ice, and it'll end up at some final temperature, which we don't know what that final temperature will be. That's what we're trying to find. But that final temperature is the same temperature as the temperature of the ice, as the temperature of the water, because these will all reach thermal equilibrium. And also the initial temperature is the same as the temperature of the water and the temperature of the ice, which is 0 degrees Celsius. So we'll start off with the calorimeter can at some arbitrary initial state of energy, EC, and then we know it's going to end up at some final state of energy, E sub C. So we'll illustrate this as a linear curve representing the change of temperature and the change of energy during this process. So during this process, the temperature change of the calorimeter will be positive. It'll increase to a final temperature, which will bring it to equilibrium with everything else. So the calorimeter will remain in its solid phase throughout this change of temperature, and that's going to be governed by the mass of the calorimeter, specific heat of the calorimeter, times the final temperature of the calorimeter minus the initial temperature of the calorimeter. Now we have temperature energy diagrams for all of the components of our system, and it's time to do something with that. Our goal ultimately is to find the final temperature of our system. And the thing that we know is, since this is a closed system, no energy will be exchanged with the environment. All the energy remains within the system. Conservation of energy says that no energy can be created or destroyed, that energy can only be transformed into other forms of energy or transferred between objects in a system. Well, for our system, if we just sum up all of the changes of energy for each of our parts, that'll be the change of energy for the lead. The lead is going to lose some energy, and it's going to give some of its energy to the water, some of its energy to the ice, and some of its energy to the calorimeter. And when we sum up all of the changes of that energy, since we are in a closed system, the sum must sum to 0. No net change in energy. So the energy exchange from the lead we called Q sub L. The energy exchange from the water we called Q sub W. From the ice we called Q sub I. And from the calorimeter we called Q sub E. This all sums to 0. So the heat exchange with the lead is given by the mass of the lead, specific heat of the lead, final temperature of the lead, minus initial temperature of the lead, plus the heat exchange with the water is the mass of the water, specific heat of the water, final temperature of the water, minus initial temperature of the water. heat exchanged with the ice is mass of the ice, specific heat of the water, because ice will transition into the water phase when its temperature starts to increase, times the final temperature of the ice minus the initial temperature of the ice. Now, the ice exchanges heat when it's undergoing a phase transition, so this is going to be plus the mass of the ice, latent heat of fusion of the ice, which is the same as the latent heat of fusion of the water. And then finally we have the calorimeter. So we have mass of the calorimeter, specific heat of the calorimeter, final temperature of the calorimeter, minus initial temperature of the calorimeter. This all sums to 0. So our goal is to find the final temperature of the system. So let's isolate T by grouping terms and putting them on one side of the equality. So we have the mass of the lead, specific heat of the lead, times final temperature, plus mass of the water, specific heat of water, times the final temperature, plus the mass of the ice, specific heat of water, times the final temperature, plus the mass of the calorimeter, specific heat of the calorimeter, times final temperature. That's the left side of the equality. Now on the right side, we have the mass of the lead, specific heat of the lead, initial temperature of the lead, plus the mass of the water, specific heat of the water, initial temperature of the water, plus the mass of the ice, specific heat of water, initial temperature of the ice, plus mass of the calorimeter, specific heat of the calorimeter, initial temperature of the calorimeter, minus the mass of the ice, latent heat of fusion of water. So let's go ahead and factor out the final temperature from the left side of the equal sign. So the temperature times the sum of the mass of the lead, specific heat of the lead, plus the specific heat of water times the sum of the mass of the water plus the mass of ice, plus the mass of the calorimeter, specific heat of the calorimeter. And that is equal to, here I'm going to factor out the initial temperature of the ice water calorimeter. So the initial temperature times the mass of the water, specific heat of the water, plus the mass of ice, specific heat of water, plus the mass of the calorimeter, specific heat of the calorimeter, plus the mass of the lead, specific heat of lead, times the initial temperature of lead, minus the mass of the ice, times the latent heat of fusion of water. So this will give us the temperature is equal to, so in the numerator we have the mass of the water plus the mass of the ice, and that is times the specific heat of water plus the mass of the calorimeter, specific heat of the calorimeter. This is multiplied to the initial temperature of the ice-water calorimeter combination, plus the mass of the lead, specific heat of lead, initial temperature of lead, minus mass of ice, latent heat of fusion of water, all divided by the mass of the lead, specific heat of the lead, plus the specific heat of water, times the sum of the mass of the water plus the mass of the ice, plus the mass of the calorimeter times the specific heat of the calorimeter. We've carried this pretty far algebraically, so now let's plug in numbers. So the final temperature is equal to the mass of the water, which is 0.100 kilograms, plus the mass of the ice, which is 0.0180 kilograms, times the specific heat of water, which is 4,190 joules per kilogram Kelvin, plus the mass of the copper calorimeter, which is 0.100 kilograms. And I'm now just realizing that the mass of the water isn't 0.100 kilogram. Rather, it is 0.150 kilograms. So I'm going to make that change right here. And then going back to the mass of the calorimeter, 0.100 kilograms, times the specific heat of copper, which is 390 joules per kilogram Kelvin, times the initial temperature of the system, and the initial temperature of this system was 0 degrees Celsius, which is 273.15 Kelvin. So the next term is the mass of the lead. So the lead is 0.750 kilograms times the specific heat of lead, which is 130 joules per kilogram Kelvin, times the initial temperature of lead, which is 528.15 Kelvin, after converting from 255 degrees Celsius. And then we are going to subtract the mass of the ice. The ice is 0.0180 kilograms, times the heat of fusion for water. So I'll write that as 334 kilojoules per Kelvin. So that's our numerator. This is divided by the mass of lead, which is 0.750 kilograms, specific heat of lead, which is 130 joules per kilogram Kelvin, plus the specific heat of water, which is 4,190 joules per kilogram Kelvin, times the sum of the mass of the water, which is 150 grams, plus the mass of the ice, which is 0.0180 kilograms. And then this is plus the mass of the copper calorimeter, which is 0.100 kilograms, times the specific heat of copper, which is 390 joules per kilogram Kelvin. So let's check our units now before we plug this into our calculator. So far, everything is looking good except for this unit that corresponds to the latent heat of fusion for water. Now, as I'm looking at this is showing units of joules per Kelvin, but actually, I know that the units for the latent heat of fusion for water is the joule per kilogram. So that was a typo on the part of the problem. Probably I made that typo in writing the problem. So those units should be joules per kilogram. And now that we have the correct units, that kilogram cancels with that kilogram. And so notice what we have left here. In the denominator, we have a reciprocal Kelvin temperature. So that reciprocal Kelvin temperature ends up being Kelvin in the numerator. So our units work. Let's plug this into our calculator now. When I plug this into my calculator, I get the final temperature of the system is 296 Kelvin. That 296 Kelvin equates to 23 degrees Celsius. So that's pretty reasonable. The final temperature of the system is higher than the initial temperature of the calorimeter ice-water combination, which was at 0 degrees Celsius. It's significantly less than the initial temperature of lead, but that's okay because lead has such a low specific heat in comparison to water and in comparison to ice that it makes sense that the final temperature will be closer to the temperature of the initial temperature of the water and ice than it is to the initial temperature of the lead. So I feel pretty good about this answer, and I'm going to box it.